All right, so I'm kicking this off. Welcome, thank you to my talk on the NYT, the New York Times games connections, and our analysis using different techniques, specifically on graph neural networks and graph-based techniques to understand the game. My name, I'm Shafik Quoraishee. My title's out of date. I'm actually a staff software engineer at the Times, and I work on our games platform. I previously worked at Business Insider, the NBA, then the Department of Defense. I have a background in machine learning, mobile development, and data science, and I have my LinkedIn and other information here in case you're interested in connecting. So let's get to the actual topic. So a few caveats that the work that I am touching on here is going to discuss. This is all my own independent research and experimentation, and not based on our internal user research, which is a different part of our research. The results of this work are generally preliminary, though we have written some articles about it, and we are doing additional experimentation. The purpose of this work is investigatory, not authoritative. So there are, again, it's an evolving understanding and discipline and area that we're looking into. So just keep that in mind. And there is third-party research with our games, not only connections, but I'm not going to be talking about those at this point. So I will. Okay, so someone can't see me, but I think that's fine. Okay, so I just wanted to say one thing quickly. We don't generate any puzzles with AI. They're all human crafted. Just needed to note that. So we'll talk about the game itself. So I'm presuming everybody here has played Connections, or people have know what the game is about in general. It was launched in 2023, and it's tested and launched in 2023. The game is edited by Winna Liu, who's a puzzle editor at the New York Times. It became one of the most played games, and second to Wordle, with hundreds of millions of plays within its first year. And again, as I emphasized, the puzzles are all human crafted. There's no AI in creation of the puzzles themselves. To the right is the actual game itself being launched. So how connections work: each daily puzzle provides 16 words to be grouped. The goal is to form 4 groups of 4 related words. Each word belongs to only one group. There's no overlap between groups, and players can make up to 4 incorrect guesses before losing the game. So the difficulty structure of connections. Now, connections, I'll get into why we wanted to or consider AI in the structure of the game itself, or the play of the game. But the difficulty structure is as follows. Yellow, there's different colors of categories. Yellow is the more obvious category, with things that are like more obviously related together. They're typically the easier words to find. Green is a slightly less, but still conceptually clear category of words that are a little harder to relate to each other, but then do have still a pretty solvable relationship. Blue is the more trickier wordplay based categories, where there's new themes and other expressions and idioms possibly involved in the word base itself for that category. And purple has the harder category. So people talk about like solving the purple category, where it's easy to potentially get the wrong word in that purple category. This is generally the difficulty structure of the game, but there are some nuances from game to game and puzzle to puzzle, which I'll talk about briefly. So why is Connections an interesting game in relation to AI? So Connections can challenge AI's ability to abstract non-obvious relationships. The game itself has intentional decoys to kind of test people firstly, but whether AI has the capability to differentiate what these decoys are. The solutions require clear, explainable categories. that is the structure of like understanding that goes into like a thing that can be repeatedly solved and tested against. And there are fixed inputs and solutions. There are answers that each game actually has, so it's not ambiguous as what the puzzle should be aiming for. And so I'll get the visual on the right has essentially a much older screen cap of a connections puzzle, being attempted to be solved by AI, and then AI struggling. Now at this point in time, that the models have advanced pretty far. That no longer is the case. That most advanced AI systems can solve connections boards, but there was quite a leap in order for that to occur, structurally and semantically. It took quite a bit of time. So that's one thing we wanted to highlight, that there was a challenge, and then in 2025 is where it took all the way up to that point since the building of AI, where it became more feasible for AI to do this, or more complex AI systems to do this on a regular. So just getting into a little bit of the thinking structure before we get into the graph structure, game structure, is how do humans solve connections? So there's the idea of system 1 versus system 2 thinking. This is a little bit of a spectrum, so it's not exactly all 100% delineated by one or the other, but essentially one type of thinking is sort of fast thinking, versus more slow thinking, where you're more deliberately considering things. So either quick decision making versus more again deliberate decision making, or more reasoning based thinking. And so usually when people are solving a problem, they're using both approaches to suss out a solution. So that's essentially how you'd approach a connections board. You'd activate some combination of the two types of thinking in your mind to assess the board. And depending on the difficulty, you may have to employ one type of thinking, reasoning, more so than if the board wasn't as difficult. And so again, there's different error cases. If you made a system 1 error or a system 2 error, it depends, you were thinking too hard about something or not thinking enough about something. That is usually leads to, in games like connections, leads to people solving the wrong categories. So there are benchmarks in connections. I just want to note that they do exist. People have attempted to benchmark that against AI and that against people solving. So this is known, and it's been known for a while. In AI in general, there's also benchmarks, but like the benchmark's important because then you can persistently test against a particular system to see if it's effective or not at solving the game. And again, older systems have been fed, groups of boards have been fed to LLMs to make them more trained against being able to solve these puzzles. And this is, again, 2025 is when the end of 2025 is when the version of this went out, and then there's more going into it for more advanced games and other things that are being worked on. But it's even the best systems still can trip up against very difficult boards. So that's something to note. So quickly, a little bit on the theory of the game. Let's talk about just basic structure. So there's certain chances of winning connections if you play the game and you are thinking about it. If you're totally guessing randomly, your total chance of winning is 1 in 63 million. If you really have no like structured way that you're thinking about solving the game. If you let's see, sorry, 1 second. If you guess one category and the other 3 categories are random, it'd still be about a 1 in 5,000 or 1 in 6,000 ish chance in solving the game, which is very low. And then if you guess 2 categories correctly, actually your chances of winning, if you completely lost in the next 2 categories, is about almost 3%. So that's sort of the natural difficulty scaling if we are operating with little information from solving each category. So I'm presuming here people have heard of the graph coloring problem. If this is a basic problem in computer science, but the graph coloring problem is essentially using a node-based graph structure, which is what this conference is about and what we're here to talk about. Involves assigning colors to vertices of a graph so no adjacent vertices share the same color. There's different versions of the problem as well, but this is a core way of approaching structurally before we add additional frills to this problem to the game. Common algorithms for solving graph problems include the backtracking algorithms, greedy coloring. There's other algorithms, but they're basic computer science algorithms too. And the graph coloring problem has applications all over the spectrum of technology, from scheduling, frequency assignment in wireless networks, register allocation in compilers, all over the. It's a very common problem. So we start off, and this is just the start of the approach. We start off by framing connections as an augmented graph coloring problem. So that means each of the 16 words in the puzzle is represented by a node or vertex. There's 4 hidden categories, which are the words that haven't been solved yet, represented by 4 distinct colors. The goal is to color each word with one of the 4 categories of colors, such that all 4 words belong to the same category, receive the same color. And then the edge can be thought of as a relationship existing between 2 words that are in the same category. So that's the basic. We haven't gone into any of the nuance or semantic structure of the game, but that's, for example, if we're building a solver to solve, we can back solve using this kind of structure. So now let's talk about puzzle difficulty, because that's where the light of the game actually shines. So we need to quantify first puzzle difficulty before we can get too deep down. What is the difficulty in the game versus easy parts of the game. So first of all, the game heavily relies on semantic relationships between words. So categorization is where do certain words form in different categories. And so there could be different word forms, word meanings. There could be combinations of word forms and word meanings, which have their own category of semantic understanding. So, for example, you will have something like phonology, or answers that that have a silent W. For example, words that fall in a phonology, same phonologistic category, are the word answer, to, wrist, and wrong. So that could conceivably be a connections category, right? Or, for example, orthographic relationships and anagram relationships, evil, live, veil, and vile, could also be related. That would be probably a pretty simple one. But again, you have more complex categories as well, which like, for example, polysemy, words that could mean a mole can have multiple meanings, right? So this is really the structure of the difficulty of the game. So we start by looking at relational alignment scores to see where the game complexity can be quantified. And relational alignment means that the categories, how related are words in a particular category. So are the words meaningfully connected in a conversation? They will have like similarity scores associated with them, which is also in some texts called coherence. Like, do groups of words coherently fall into a category? So if 2 words are highly aligned relationally, they the model, or anything that is reading those words, can comprehend those words more easily. There's different types of scores. There's some basic ones like Levenshtein distance or cosine similarity. They're mostly evaluated using natural language processing, using word embeddings, topic modeling, other techniques in NLP, which help allow these scores to be quantified. And they have there's different components, which I'll get into the next slide, of semantic similarity. So there's not just one score that says these 2 things are related, because again, there's multiple dimensions of alignment between words. So comparing relational alignment and scoring between puzzles, the reason why we have this number is so that we can validate difficulty of a puzzle. So here's an example of an easy puzzle. And with the easy puzzle, there's a high coherence score between the words versus a harder puzzle, which has a lower coherence score. Again, this is what we're tending to. There's much more nuance in those alignments, but we'll continue down the path. And then over time, you can see that there's the difficulty of puzzles changes in terms of coherence, because you can see that there's a graph mapping the coherence in each of the categories. So over like several days, for instance, or several weeks or several months. So this is an example. This dip here is just because the puzzle was missing. So it's just kind of a funny thing. But the key thing is that you can see a fluctuation. So again, because we're talking in a multi-dimensional world, we have multi-dimensional relational alignments we need to consider. So we have different categories of scores. So this is a radar chart, if you're familiar, and essentially different alignment scores will show distinct representations or strengths in particular axes, as you can see. So some the words that have a functional relationship in one category may be very strong versus another category. The functional relation might be weaker, but some other relationship like domain-specific knowledge might be stronger. And so again, this is the way of understanding the multiple relational alignments that are needed to kind of figure out how tricky a graph is to a system, or how tricky a connections board is to a system. And so again, there's different distributions of the relational alignment scores, which we can compute against different boards. This is a tool I built to do that, just so I can have sort of like an understanding of like where word difficulty is, because using something like this, we can then condition a model to have a similar, in theory, condition a model to have a similar understanding of word distribution difficulty for categories, like in connections. So now, how do we build a better solver or an optimal solver? An optimal solver, that's kind of tricky because we already have solvers that perform pretty well. But the way that I approach solving is from a graph perspective. And the reason I did this will sort of become clear. We build we start off with a conceptual semantic graph of the words. So we already have a graph relationship from the coloring problem. We convert it to something that has more of a human understanding of the relationship between words. So if you're familiar with WordNet or ConceptNet, I don't know how many people have seen that before, but WordNet and ConceptNet are those are two different ontological databases of relationships between words. So for example, WordNet will have things that are like in the same category, like hypernyms or hyponyms, or any of those taxonomic relationships that I showed you earlier. And ConceptNet will have the relationship between these two words. So for example, milk is related to a cat in a certain way, dog is related to a cat in a certain way, a mouse is hunted by a cat, so there's a relationship there. A cat is a cat, a part of a cat is a claw. A cat can be used for a pet. So these relationships are crucial to having the machine have more nuanced understanding of how to how to parse categorical relationships and sort the words into the correct categories for the game. And so we convert these to word embeddings for the machine to understand. So we talk about the property graph. I'm not going to go too deep into the property graph itself, but the reason for creating the property graph is to essentially have those relationships created into properties that can be magnified by the relational alignments that we were just talking about. So when you have these graph distributions, you can see that there's a strength between different categories, and including the misdirection categories or misdirected words, because some words again are meant to throw people off, and you might not be sure if a word belongs to one category or another. So building this as in this property graph with the graph topology could help a machine that's trying to understand know the difference between what could be a red herring versus not. So next, we'll just quickly touch on reinforcement learning. I know I'm going through a lot of different topics, but no one said that this kind of AI stuff is, even for an easy thing like connections, is easy. So that's just something to keep in mind. So reinforcement learning is basically a paradigm in AI where a system learns by interacting with its environment. So over time, a machine can start off pretty bad at a particular task, and then over repetitive interactions, it can get better at that task. And so there's a lot of factors that go into reinforcement learning, but what the visual on the right that you see that I constructed is the so-called cart and pole problem, where there's a AI-driven cart that's trying to balance a pole, and it gets better over time, but it fails a lot in the beginning, similar to how a car is driving on a racetrack. It needs many iterations if it's AI-driven before it can get the curve of the track correct. Now, why that's important is because that's essentially how we needed to approach solving connections as the game. So first, before since this is a machine learning problem, we went down building a training and test set. So building a training and test set required making sure that we go through various training and test paradigms, which includes stratified sampling, putting categories into putting boards into tiers of categories, and having some easy puzzles, medium puzzles, and difficult puzzles separated out so that the puzzle strategy that the AI would take would be smart enough to figure out which strategy to which brain to switch to, so to speak. So that's the idea of a tested training. And then to build an optimal solver, we needed to essentially try to build, go towards, since we are representing this as a graph problem, using graph networks and Neo4j, etc. We use a custom graph neural network, which I call it RGCNN, with reinforcement learning to evaluate and rank similarity metrics. So what happens is that this is a neural network specific model. We train the AI to select word groupings based on dynamic coherent signals, and then the AI again goes through the training process and eventually updates its understanding, and that's the typical back propagation that many people who are familiar with neural networks understand, but this is from a graph neural network particular perspective. And then we check the evolution of the graph over time. I'm not going to go through the details of the system itself, but this is kind of how the system structure is at the higher level, including the persistence layers and feedback loops and other things that go into building this agent that we built out to test this process. And again, system diagram piece. But essentially, this is the visualization of the cluster formulation of the words. So basically, the graph neural network essentially tries to group that based on these scores. We talked about relational alignment scores. It learns the best alignments and tries to group the structures into different categories. There's 5 here. There should be 4 for each category, but the 5th one represents unknown information that's still to be evaluated. So that's just kind of how the morphology of the system evolves over time as the neural network is learning, the graph network is learning. And so the dynamic updates of the graph structure is based on the feedbacks, incorrect versus incorrect guesses that the machine does over time in its reinforcement learning process. And again, sort of there's a more blown up view or hyperdimensional view of how what occurs here is that different clusters are sort of learned, and then the agent tries to perform on each of these clusters for a particular puzzle. And so the same, again, these are based on the difficulty groups in the connections board. And so the ball represents the learning process and the optimal RL process in the space for the machine to actually get to more like best fitted state to solve the particular board. So there are some scores, and again, this is different than the LLM version of the solving strategy. But again, we're evolving this and experimenting with this for more general cases and trying to understand more about how a system like this evolves for different things other than connections. We have performance ways of evaluating performance, which includes some standard metrics like grouping accuracy, which an example is as an NMI score. And the whole point is these are supposed to get better over time to reduce uncertainty of the system. And again, why do all this? LLM is essentially a black box. They're great. Agents are great. Agents can solve a lot of things. But we essentially wanted to build an understandable system grounded in human principles to be able to solve this game. So using a graph neural network structure, we are able to ground this more in human ontological knowledge to help it solve the game more as we would, using our own vocabulary and understanding. Also, that games like this are like, are similar to benchmarks that are being built, like are the AGI benchmarks and other benchmarks, to actually determine how human AI intelligence evolves, because AI intelligence it still has limits, and those are all grounded in something called Moravec's paradox. But here's some of the work by the first article is by myself, which I've written, and then there's some benchmarks in other articles out there which you can take a look at. And if you're familiar with Moravec's paradox, that's where I leave you, where the AIs are great at doing certain things and amazing, but they're challenged at doing simple things that humans can do. So that's an example of that. And so we have some next steps, but I'm at time. So I will leave the open for questions, if there are any, leave this presentation.